All right, everybody. So, thanks for coming to this talk. I'm really excited to have Rohin here. Rohin works as a research scientist on technical AGI safety team at DeepMind. He completed his PhD at the Center for Human Compatible AI at UC Berkeley, where he worked on building AI systems that can learn to assist a human user, even if they don't initially know what the user wants. He's particularly interested in big picture questions about artificial intelligence. What techniques will we use to build human-level AI systems? How will their deployment affect the world? What can we do to make this deployment go better? He writes up summaries and thoughts about recent work tackling these questions in the Alignment newsletter. Here is Rohin. If you have any questions, Rohin is happy for you to put your hand up during if you want to clarify anything. But there is an AI Q&A later in the day that you can go to ask more sort of exploratory questions. Cool. Over to Rohin. Thank you.
Cool, yeah, thanks for that introduction. And yeah, so prior to my life in AI safety, I did a lot of teaching. I was very excited by that. And so this talk is more like a teacher's talk than a talk. And among other things, that means you should really feel free to ask clarifying questions. I would much rather get through like 2/3 of the slides, but like make sure people understand them, rather than get through all of the slides with all of you not having any idea what's happening. So yeah, I will pause at many points asking for questions, but also feel free to just raise your hand. I may not immediately call on you, but hopefully I will not entirely miss you. People in the back, you can hear me? Great, excellent. All right, first teaching technique that is not in a talk. I am going to do a poll I'm going to name some terms. I want you to raise your hand if you have like a vague idea of what this term is. This will help me target my talk to the audience I actually have. So first term, machine learning. Okay. Python, the programming language. All right. PPO, or proximal policy optimization. Actually, surprisingly many. What was the other one I was going to do? Oh, convergent instrumental subgoals. Okay. All right, sounds good. So based on that, this talk is going to be split into roughly 2 parts. The first part is, all right, maybe more classical arguments that people may have already heard already. I will call this the philosophy section of the talk. It's the sort of thing that, it's the sort of arguments that you can make ahead of time without really delving into the details of AI machine learning as practiced today. You can sort of like do this sort of reasoning from your armchair and get somewhere with it. But I also think that this does not really get you as far as you can, and to actually like do good AI safety research, you do need to understand more of the details that are going into the actual systems that we're building today. And so the second portion of the talk will be more about that, and is probably the longer portion of the talk as well. But yeah, so to start off, philosophy. Okay, so I think the core argument in the sort of philosophy side of AI safety is that it's very hard to specify the thing that you want. Like, in some sense, if you're trying to build something smarter than you, that's going to then optimize everything about your life. What you want to be doing is specifying in every possible situation what is the right thing for that AI system to do. And this is like a huge thing. There are just so many possible ways the world could be, so many ways the world could be steered, many things that we haven't even considered yet. And somehow your specification has to be telling the AI system, has to have the information such that the AI system can deduce what is the right thing to do in all of those possible situations. Turns out humans are like not good at this. Let's look at some examples of that. One is just, This is this famous example of King Midas, who asked to, have everything that he touched turn to gold. Of course, then he goes and like can't eat any food because it all turns to gold. Accidentally touches his daughter, she turns to gold. Obviously not the thing that he actually wanted. Presumably he wanted the voluntary ability, or the ability to turn it on and off or something like that. And then of course we have lots and lots of stories about genies and how they like literal wishes for genies don't exactly work out. I quite like this example. Yeah. Okay, so that's just like pop culture or something, or maybe it's not exactly pop culture, but culture in general. We've also got some examples in actual AI and machine learning practice. So this is a pretty famous example from OpenAI. And if I press this, does it play? No, it does not. Okay. Let me move the mouse here. Yeah. So this is an example of a boat racing game called Coast Runners. And so this AI agent was trained to maximize the score, which you can see in the bottom left corner. And the intention was for the AI to learn to win the race, win the game. But what it instead learned was, hey, these green boosts, they give me 1,000 score every time I get them. So I'm just gonna like go around, crash into the wall, turn around, and get these boosts forever. And this is actually just a really good way to get score. So it turns out the specification of like maximize your score did not actually lead to the thing that we wanted it to lead to. Oh my god, where's my mouse? All right, there we go. Onwards. So here's another example, also from OpenAI. Well, actually, this one was a joint OpenAI DeepMind project, but I got it from the OpenAI blog post. So this is an example where this robot hand, which is maybe a bit hard to see, but there's a robot hand over there, and it's being trained to like grasp that ball. And it's being trained using human feedback. So a human looks at the robot trying to grasp the ball and says, yes, that was good, or no, that wasn't good. That's like not technically true, but you can imagine it being basically that. And at some point, they trained it to show this behavior, which maybe looks good to you, but actually what's happening here is that the robot hand is, like, if this is the ball, and this is the robot hand, it's doing this. And it turns out that the humans who were providing feedback there thought that actually the robot hand was successfully grasping the tennis ball, and so we're like, good job, you grasped the tennis ball. And now, of course, the robot is just sort of like not actually grasping the tennis ball, and again, it's doing something we didn't want. It's more obvious here because of the vertical and horizontal white bars. They added that after noticing this problem in order to allow the human feedback graders to actually understand what the robot was doing. Cool. All right, so that we've seen, like, hopefully by now you agree with the point that, like, it's pretty hard to actually specify what exactly we want. But I've shown some like kind of toy examples. Nothing terrible happened in those examples. So what goes wrong in a superintelligent case? So specifically, I want you to imagine that we've got smarter than human AI systems. We're going to use these systems for some like pretty broad real-world tasks, but we still haven't solved the specification problem. So we still are like giving these specifications that don't exactly narrow down on the behavior that we actually want. So what happens? Okay, I'm going to be even more concrete, so you have a specific scenario to think about. We're going to imagine that we fail really, really badly at the specification problem, so that the specification that we implicitly communicated is make as many paperclips as possible. This is not meant to be realistic. This is meant to be a thought experiment that to give intuition. So how bad can that be? Teaching moment again. You have 2 minutes. Discuss with the people next to you. Go. You've got 10 more seconds. All right, let's come back. All right, can I get 3 brave volunteers to name one thing that could happen in such a scenario? I'll also accept cowardly volunteers. And it'd have to be brave. Yes?
The AI buys a bunch of iron mines.
Yep. The AI might buy a bunch of iron mines in order to use all of the iron in the world to make paper clips. Sounds correct. Yeah.
We went on a big step up. We went, okay, all materials, or all metal resources are gone. And we're like, well, you know, we're putting other resources towards making metal. What if they start making paper clips out of other things? And then we were like, okay, well, maybe humans are getting in the way of making paper clips because we're not making paper clips all the time. So essentially, the world becomes a giant paper clip filled with paper clips.
All right. Sounds like everyone managed to hear that, so I won't repeat that one. Yeah. Yes, we could. Yeah, we can see how small exactly how small we can make paper clips. I don't know. Maybe you could get by with like 15 atom paper clips to get the shape right. Yeah, seems plausible. And then we make lots and lots of 15 atom paper clips. As that maximizes the number of paper clips. Yep. Cool. So in the interest of time, I'm going to move on. But yeah, so as I'm sure many of you correctly reasoned, a very broad, big objective like this tends to lead to like some pretty extreme outcomes. And I think the more general observation you get out of this is that for most big, broad, ambitious goals like this that an AI system might end up having, you have various convergent instrumental subgoals. And what this name means, subgoals, means that it's like an intermediate goal that the AI is pursuing in the process of achieving its actual goal. Instrumental, same sort of meaning basically. It's that it's not something that the AI wants for its own sake. It's something that the AI wants to achieve because that would help it achieve with the actual goal it has. And convergent, it means that, you know, the AI system is very likely to pursue the subgoal just because any plan that is effective at achieving the goal tends to also achieve these subgoals. So let's look at some examples. The AI system will want to stay alive in the sense that it wants to continue operating in the world. If you're not operating in the world, you can't achieve your goal. Or as Stuart Russell has put it, you can't fetch the coffee if you're dead. It wants to become smarter and more capable. Turns out, usually if you're smarter and more capable, you are better at achieving your goals. By the way, these are also convergent instrumental goals for EAs and humans, so you know, consider optimizing for these yourselves. Not all of them. The later ones are bad. Don't do those. Prevent its designers from changing its goals, or as we call it in the EA space, value drift. Seems kind of bad. You know, from the perspective of your current goal, if you have a different goal in the future, well then you're going to do different things. That's bad for your current goal. The current goal won't get achieved. Gain resources and power. This is basically the same thing as number 2. You want to trick humans into thinking that the AI system is actually helping them so that they don't do bad things like shutting the AI system down. Or if you've got enough power and the humans can't actually stop you, maybe you overpower the humans so that you can then go and like make all of your paper clips without having the humans be obstacles to your progress. And this is really the reason that we're worried. It's that once the AI system and the human get into this adversarial relationship where the AI system has some goal and the humans don't want the AI system to be pursuing that goal, then all of these sorts of things happen, and especially the last 2 happen, and that seems pretty bad. It seems like it could lead to arbitrarily bad outcomes, including existential catastrophes. Cool. So the takeaway of this philosophy section is that a sufficiently superintelligent AI system that pursues an inadequately aligned goal would lead to an existential catastrophe. And I think I'm going to pause here for any clarifying questions. Yes? Yep. So to repeat the question is why do we assume that this level of superintelligence is possible? And like we're clearly assuming like extremely high intelligence. That's the next part of the talk. So that's part of it. I will mostly just defer to there. But one argument that I do want to make is that like it seems very surprising if in principle human intelligence is the maximum level of intelligence that we could get. Like in some sense, we should be like the dumbest possible creatures that evolution could have created that could then create more intelligence, because evolution is way slower than we are at building more intelligent things. So I would really expect that in principle it is possible, and then there's a question of when we get to it, and that question I'll leave to the next part of the talk. Other clarifying questions? Yes? Yep. So to repeat, the question is what happens, where do I think if the AI system is improving its goals over time, where do I think those goals ultimately lead? I am going to punt on that question on the grounds of it not being a clarifying question, sorry. Yes?
In many of these cases, you have this AI starting overriding the human interests. And I'm just wondering, most basic machines, you have them already have some kind of a decoupled process override from the outside. How difficult is it to consciously implement that in the AI system, saying, okay, now you're doing already, we're gonna shut off when something's supposed to fuck. I mean, how difficult is it in an override function?
I think this is pushing the bounds of what's a clarifying question, but I'll answer it anyway. The question is, can we put an off switch on the AI system? Why would that not work? And so I would say fundamentally the problem is you're in an adversarial relationship with the AI that is trying to prevent you from turning it off. And as to an actual strategy that the AI system could use, one simple strategy that I imagine is the AI system continues to behave as though it's doing the thing that you want, but surreptitiously is like looking for zero-day exploits into other computing systems. Once it finds one, it hacks into those other computing systems, creates copies of itself that are running autonomously there, and your off switch doesn't work on those copies. Yes?
Could you say a bit more about what you mean by system pursuing the goal that explicitly represents and maximum potential?
Yeah, so the question was, can I say more about what it means for an AI system to pursue a goal? Does it have to explicitly represent that goal? It does not. I agree that this is a sort of difficult thing to. I don't think we have a good handle of what it means to pursue a goal. I definitely don't think it needs an explicit representation. I don't think there's like an explicit representation inside of human brains of like, I don't know, the long reflection and various other things that we talked about in EA, but I would nonetheless say that like we are pursuing goals that include things like the long reflection. But mostly I would say is like, if the AI system is taking high impact actions on the world, if it's like funneling the world into like a small set of possible states, then it like really matters which small set of states it's doing. And that's sort of what intelligence is. It's the ability to like take this like large space of possibilities for what the world could be and then funnel it down into the states that are the ones that you're aiming towards. And that's mostly all that I mean by pursuing a goal here. I still am not super happy about that characterization. I think I would like AI alignment research to do better about being more clear about what exactly pursuing a goal means, but that's maybe my best answer for now. All right, last clarifying question.
How do you specify a sub-goal without having a primary goal?
So the question was, how do you specify a sub-goal without having a primary goal? I don't think you can. I'm imagining that there is a primary goal. I'm not imagining that we specify sub-goals. I'm imagining that we specify primary goals. And I'm saying, suppose we fail at specifying primary goals. Does that answer your question? I feel like I misunderstood it. Okay. All right, I will continue on in the interest of time. Cool. All right, so we've done the philosophy section. I think there are a bunch of other questions, some of which we've touched on how we get from this philosophy argument to like, and this will actually happen in the real world. Here are some examples. I'm maybe not going to spend too much time on them. I think like the big thing about these questions is that they don't really get at the core. They don't really get at the core worry, which is that like AI systems that are pursuing goals in the sense of like aiming at a narrow set of states of the world, like we need to know what we need to have control over the set of states that they're pursuing. Like none of these questions are really like, yes, this is how we have that control, or like, oh yes, this is why we don't need to do it in the first place. They're just like more meta-ish questions about like maybe we deal with it in the future. I would like us to have an actual reason, and like maybe we find that reason in the future, but let's have a reason to believe that we're gonna find it in the future or something, and actually do the work for finding that reason. But yeah, so I think in general, this, both to answer these sorts of questions and to just make progress on understanding the philosophical argument better, what you want to do is just have better models of how AI systems work, how you build superintelligent AI systems, and so that's what I want to talk about next. Specifically, I'm going to talk about a threat model, and at a high level, a threat model is just a story that starts from now and ends with existential catastrophe. And I usually split these into two different parts, here's what a story could look like. This is a very bad story, to be clear. But a story could be, we're going to do gradient descent on training data in order to train a neural network, and that neural network is going to be AGI, because for some reason it's going to be AGI. And then the AGI is going to be misaligned, and so it's going to get a bunch of humans to argue with each other, and then they're going to start nuclear war and we die. That's a story you could tell. It's not a very good story. I didn't really give any argumentation for any of this. But that's the sort of thing that I want to do, except better. In the story, I would say that like, I split this up into two pieces. One is the development model, which says like, from here, from where we are now in this world, how do we get to AGI? That's the development model. And then there's a second part is like, once we get to that AGI, how do we then get to existential catastrophe? And that's a risk model. And like, obviously you should have the same notion of AGI for both of these pieces. And that's actually like a pretty hard thing to do. And a thing that I really look for in these stories. Cool. So let's first talk about a development model. Or actually, clarifying questions just about what a threat model is. I'm only going to take one. All right, onwards. So my development model that I'll be talking about this time is just scaled up deep learning. And as a background assumption in here that I'm not going to argue for, I'm going to say that intelligence is just a program, in the sense that, there's no like extra metaphysical component that makes things intelligent. If you manage to figure out the computation that neurons are doing in the human brain and then replicate that computation in a computer system and also replicate the inputs and outputs, to the brain, this would be a very difficult challenge. But if you did it, at that point, you would just have an intelligent human brain, sometimes called whole brain emulation. There's an assumption. There's no other magical weirdness that's also needed. That's an assumption I'm going to make. I understand that some people debate it. I don't really understand these perspectives. I'm not the person to ask. Cool. So my key claim in this section is that what we need in order to get AGI is a large effective search over an expressive space of programs with a very stringent goal that only allows for the intelligent programs to succeed. Cool. So I'm basically just going to be talking about this for the next 15 minutes or so. So to get a bit more sense of what I mean by this, let's look at the case of evolution. And so hopefully everyone agrees that evolution is not in any sense intelligent the way that humans are intelligent. Evolution just tries random shit. It might take a fly and decide to have it grow legs out of its face. That's a mutation. It'll just try it. It will have no particular reason for trying this. It's not intelligently thinking about maybe legs would be great if they grew out of faces. It just tries it and sees what things work. It's really not intelligent. Nonetheless, evolution did in fact produce humans. Humans are in fact general intelligences, so I claim. So how did evolution do it? I would say that basically it's just the same thing from the previous slide. There was a large effective search in the sense that, every generation, evolution had some number of mutations. There were a bunch of different new creatures that were created. And it was effective in the sense that it got some incremental feedback on how good those mutations were. Some of those organisms survived and reproduced more than the others. It's not very good feedback, but it did get feedback at all. So, I say effective, it's not that effective, but it was at all effective. It wasn't like it got literally zero feedback. There was an expressive space of programs, namely the strings of DNA, which are just gigantic, and you can make lots and lots of changes to search for lots and lots of different kinds of organisms. And there was a stringent goal, which was to outcompete other organisms. Maybe it's a little bit sketchy to call this a goal because it changed over time. Initially the goal was outperform algae that are taking sunlight and doing photosynthesis with it. And then later on it's make sure that you don't get eaten by tigers, and one of these is easier than the other. But the point is, every time that evolution found a better program or a better organism, then that would spread out, and then this would make it harder to survive and reproduce, and thus the goal became more stringent, and you had to go ever onwards to more and more competent programs in order to do better. And turns out if you do some insanely large amount of this, you eventually get to humans who are in fact generally intelligent. Cool. Actually, questions about this? Clarifying questions only. Yes? I think I'm going to punt on this question on the grounds of it not being a clarifying question. Sorry. Clarifying questions are things where you're like unclear on what I said. Yes?
Yeah, so are you saying that those three are necessary conditions for the development of intelligence, or those three are necessary conditions for intelligence?
I am saying that these are, I'm not saying necessary, I'm saying these are sufficient conditions for the development of intelligence, not for intelligence itself. You can, yeah. Intelligent behavior itself is like some totally different thing. Yes?
Would it be like one of the sayings of sufficient conditions for optimization courses that can produce intelligence?
Yes, I'm happy to say that these are sufficient conditions for an optimization process that produces intelligence. Yes? So the question is, what effect does the environment play? I would say that the environment is baked into this number 3 over here, about there being a stringent goal. Like the reason that evolution had to keep increasing the competence of the organisms that it produced was because the environment kept having new and different ecological niches that the organisms had to become better in order to exploit. Does that answer your question? No. You could see it as the environment changing to produce the effect of better organisms rather than the organisms. I agree that is also a valid way of looking at it. Yeah, maybe I don't understand why that matters, but I agree that is a way you could look at it. Sorry, we can talk later. I'm gonna move on for the sake of time. Cool. All right, so how do we apply this to neural networks? I'm going to claim that for neural networks, again, what we need is a large effective search. So this basically means a lot of compute and a good training setup such that you actually get feedback after every gradient step. You don't just like randomly search through the space and get feedback only at the end. The second thing is you need an expressive space of programs. That's going to be large neural networks. And then you need a stringent goal. We'll talk a little bit more about what that is in the context of neural networks later in the talk. So to go a little bit into the first 2 points, let me give a brief, very high-level overview of deep learning. So in deep learning or neural networks, those are basically synonyms. You've got this thing, it's a neural network. It wires up the inputs that it's getting to the outputs that it's supposed to produce. So like maybe its inputs is like a picture of a handwritten digit, and the output is like probabilities assigned to each of 0 through 9. That's what you would use for the MNIST classification task. And then in between the inputs and the outputs, there are just a bunch of numbers that are wired up in a certain way, and you can just assign some numbers into these intermediate nodes, and then that defines a program. And different numbers will usually lead to different programs. So that's the basic setup for a neural network. And then here's one way that you could do learning. This is not the actual way that we do learning, but it's like, it would work, it would just be less efficient. So you just start with a random program, you put some like random numbers into the neural network. Then you change the numbers a little bit, and you look at the new program, and you're like, hey, is this new program better than the previous program I had? Does it give the right outputs? Does it give better outputs for all of these handwritten digits than the previous one? If yes, then I'm going to keep it. Otherwise, I'm going to revert back to the previous things that I had before. And then you just repeat this for a long time, which is not actually that long in calendar time because computers are really fast. And then eventually you get a thing that's really good at predicting what handwritten digits are. Again, actual learning on neural networks is a little more complicated. There's this thing called gradient descent. But this is a pretty decent model, and if you actually just ran this, it would work, just maybe taking some significantly longer time. Cool. And so, you can see how this is like a large effective search, where large is just a lot of compute. Effective is every time you change the numbers, you get a bit of feedback on whether the change was good. And expressive space of programs is because there are just a ton of numbers for you to possibly change. Okay. All right, so that's like points 1 and 2, and how they apply to neural networks. And I'm going to talk about point number 3. How do you get the stringent goal? A goal that is like so strong that only intelligent programs can do it. There's no other cheating way to do it. I'm going to claim that what you need is diversity. So if you imagine that in this diagram, you've got like, you know that you can get information like the point that I'm looking for is on such and such line. If you only have one line, then like you don't really know exactly which point you're looking for. You might just get some random one. But once you have a like set of lines that aren't like all basically the same line, but there are a bunch of them coming from all sorts of directions, and they like really do just narrow down the point to like only one thing. And that's sort of the intuition for why diversity is good. It like throws away a bunch of programs that could have been good, but then you're like, oh no, it doesn't work with this new diverse data. And it forces you to narrow down in on only the intelligent program. Yes. And yeah, it just gives you robustness. It turns out that it's pretty hard to get sufficient diversity, so there are lots of examples of us failing at this task. So, for example, there's this great example of a neural network that was trained to predict which patients should be hospitalized, sorry, it was trained to predict whether patients would recover from an illness that they had, and this neural network was like, by the way, if your patient has had a history of asthma, then they're way more likely to recover, which, most people would recognize as obvious nonsense. Why did the neural network do this? Because it was trained on like patients that, were sent through the medical triage system, and it turns out the medical triage system, anytime it looks and sees that a patient has a history of asthma, I think this was for like flu infections. So if they see that there's a history of asthma, they're like, oh God, we should really take care of this, and they like put them on significant treatment options, and so those patients are more likely to recover. And the neural networker is like, great, asthma is a good signal about like patients' health. Yeah, this is a cool example from reinforcement learning. This is a game called Coin Run. The agent there is in the bottom left. The goal is to collect the coin that's up there in the top right corner. During training, the coin is always at the end of the level, and so you then train this AI system. It's really good. It like dodges all the obstacles, jumps in all the right places, collects the coin. I think it succeeds 95% of the time in the experiments we ran. And then at test time, what you do is you take the coin and you move it to like somewhere in the middle of the level, and the agent just completely ignores the coin. It like runs around, jumps over all the obstacles, jumps over the pits, and then runs to the end of the level and jumps up and down over there, as though like asking, where's the coin? But like what's actually happening is that your data was not diverse enough. From the agent's perspective, you could have just been treating it, hey, go to the end of the level, not collect the coin, because there wasn't enough diversity in the coin position to rule out the go to the end of the level program. And it turns out that in this case, it learns to go to the end of the level program. Similarly, this is a cool example from some interpretability work where they found that there was a neuron that responded both to like the red seams on a baseball as well as the like gums of a shark. And so then they like took this example of, I believe this is a whale, and they were like, well, if we just like put in a baseball, then it's going to think it's a shark. And indeed, that's exactly what happened. So like there wasn't enough data to rule out the, whale plus baseball thing from the sharks. But you know, despite the fact that diversity is hard, there are in fact lots of successful examples of big diverse training data sets leading to good results. So some examples, this is Xland, a recent publication from DeepMind, where they trained agents on a wide variety of possible goals, and then they showed that they could give some new handwritten, human-written goals at test time, and the agents would just, in fact, successfully pursue those goals at that time. This is OpenAI 5, where the agents were trained over millions of games to respond to all sorts of strategic situations in Dota, and then they work really well. And in fact, they're sufficiently robust that even though they were only trained to play with and against other AI agents, you can actually take the team of 5 agents, replace 2 of them with humans, and it mostly works. They still operate reasonably well. They don't just go crazy. This is an example. This is large language models. This is GPT-3, where you just train an AI system to be able to predict all of the text of the internet. Well, not all, but text from the internet. Turns out the internet is a very diverse source of text, as you probably could have guessed. And then the resulting system has all sorts of abilities, because all of those abilities were needed in order to predict the internet text very well. Anything without those heuristics would have just not been sufficiently good to predict internet text. This is, again, the same coin run example. One thing about the coin run example is the actual levels. So the coin was always at the end of the level, but the level itself, where the pits are, where the enemies are, that gets randomized every single time. And so there was this interpretability work that showed that actually the neural net has neurons that visually identify the things that are randomized during training. So intuitively, because of that randomization, there was enough diversity that it forced the neural network to learn visual concepts for things like enemies and so on. This is an example from multimodal, is this multimodal? This is an example from multimodal models where they found that there were these neurons that would respond to both English words like shocked and also pictures that kind of look like a shocked emotion. And so it turns out if you have sufficiently large, sufficiently diverse training data set from both text and vision, then your neural network is forced to learn these concepts that connect the two together, because that's how it can make good predictions. All right. So I will claim that for the stringent goal, you need a very diverse data set. Questions about that? Clarifying only. Yes.
With regards to the actual goal, what data set is used for, what role does that play? For example, in predicting the next word, which is kind of trivial in the data set, but sometimes the actual goal might be important.
Yes, I agree that, so the question was shouldn't this all be with respect to the actual goal that you're trying to do? And my answer is yes, in some sense. I'll talk a little bit more later about how you actually get these systems to then try and do something that is what you actually wanted. But here I'm not worrying about the goal very much at all. I'm just saying you can use any goal that you want as long as it's stringent enough that it forces only intelligent programs to work. And then later we're going to do some other stuff that makes sure that it to fine-tune it in order to actually doing the thing that you wanted. Yeah. Yes?
Does the data set refer to the training set or the test set, or both?
Training set only. Because the training set is the thing that actually constrains your program, because you never actually change the program based on your test set. So this is always the training set. Yes? I can't hear you. Can you speak up?
Would you say it's true to go
So the question is a stringent goal a sufficient level of compression over the state action space? That's reasonable, but you also have to talk about what the state action space is. But within that, yeah, I think generally the like intelligence is compression view seems correct to me. All right, onwards, because I do not have much time left. I'm going to skip this slide. So one thing that you might worry about given this argument that I've made so far is that I've said you need a large effective search, but I've argued for why this sort of thing should in fact work with some level of largeness. But how large does it have to be? Like maybe it's just so large. Like evolution was huge. If that's our upper bound, like maybe it's just infeasible, or lower bound, sorry. And there I would say, take a look at this draft report on AI timelines from OpenPhil by EAGxOxford. It like tries to actually have some quantitative estimates that in the end, I think the report ends up concluding with a median of about 2050 for transformative AI. But really I would say it's about like quantifying how big a search in this model you would need. Cool. So far we've talked about the development model, and the next step is to move on to the risk model, which is now that we have the story for how we build AGI, how does that then lead to an existential catastrophe? And recall from the philosophy section that the way that you get an existential catastrophe is if your AGI system is pursuing an inadequately aligned goal. Yeah. So that's what we're going to try and talk about now. So first off, I need to answer the question I got asked just a little bit ago of like, how do you actually make the AI systems be useful to you if you're just doing these like random goals, like predicting text on the internet? And my answer here is that like, you've first done this pre-training step where in this case, this is like predicting the text of the internet in order to create GPT-3. And then after that, you want to do a fine-tuning step where you take your actual goal, like maybe you want your GPT-3 to summarize articles. So you have a human who like looks at possible summaries that GPT-3 writes and says, hey, this one was better than this other one, and then you use that to train your AI system to do the thing that you actually want. And the idea is that this can be done fairly quickly because your AI system already has all of the concepts. You're more just like telling it, hey, by the way, you should do summarization now, rather than trying to teach it the entire task of summarization in the first place. So I'm going to assume that we're going to follow this basic paradigm. And so then the first way you could get a bad goal is that your fine-tuning reward could be wrong. And in particular, you might have cases where like your humans give feedback that encourages bad behavior. Yes. So here's an example of that. Let's say you're training your language model, and it's like really competent, very powerful. It is correctly convinced that COVID was caused by a lab leak. I don't know how it figured this out. I don't know whether COVID was caused by a lab leak, but somehow the AI model figured this out. And then it's like, and then it says this because, I don't know, it's trying to tell the truth at this point. And then the human providing feedback is like, oh, no, we don't say that here. We don't know whether or not COVID was caused by a lab leak. You should be appropriately uncertain and just say that the answer is that we don't actually know yet, but that is a plausible hypothesis. And if that's the feedback that the model gets, well, it's going to learn that what it's supposed to do is to say what humans think rather than what is actually true. So that's one way that things could go wrong. Another way that things can go wrong is what I call objective misgeneralization. So this happens when you get enough diversity to get a model that does what we want during training, but does something else during deployment after some distributional shift. So as a simple example, let's say we train a really powerful AI system with human feedback, it's not obvious that we get data distinguishing between the following 3 models. One is like the aligned model that actually does what we want. The second is a model that knows that it's an AI agent in a training process, and its goal is to maximize the number that in the memory cell that corresponds to the reward. You know, that's totally consistent with all of the training data it ever receives. And the third one is the model that knows that if it does anything other than the thing that we want it to do, we're going to turn it off. But actually what it wants is to maximize paperclips or some other goal like that. It too is going to behave exactly the way that we want during training. And so the gradients, the training process, the gradients there are not going to change the model and prevent it from being this. Cool. And so yeah, with that, I've reached the end of my talk. Here are the key takeaways, and I don't think I have time to take questions, but yeah, thank you for listening.